what's a very basic crypto that Bitcoin kind of depends on. There we go. And cryptography as a whole, we hear cryptography, we hear Snowden, we hear Tor, we hear all this stuff about hiding data. But Bitcoin kind of does the much less glamorous, or maybe more glamorous, depending on your inclination side of crypto, which is about making sure data comes from people you think it did, and making sure things can't be changed after the fact. Because all of Bitcoin, other than maybe your local wallet, nothing's encrypted, but everything's still secured. And there's really two mechanisms by which it's secured, which is hash functions and signing. And, well, what's a hash function? If you remember from high school when they showed you function diagrams, you probably had some little circle here and a circle here, and your numbers would go map from one input to the function and the output. So we'll say that's f of x. And your teacher probably drew some diagram like this. Well, with hash functions, again, what we're interested in is mapping, but the input, I'm gonna erase it. There. So your input to the hash function, that's an infinitely large circle of all possible messages, and your output here, well, this is something like 2 to the 256. And it's like, if you go give me a message, well, if I run it to the hash function, I'm basically taking a random number, but just for that message, out of that 2 to the 256 possibilities, and mapping it. This is why, in cryptography, when they're trying to analyze hash functions, they use the idea of random oracle. So you imagine it's the oracle you go to at the temple, and you submit your message, and you say the little prayer, and the oracle spits back a random number. Well, as long as the oracle does the same thing every time, you have a hash function. And this is kind of cool because, well, if this space is infinite, as in any possible message can be hashed, and this digest is really big, well, can you count 2 to 256? 2 to the power of 256. That's more atoms in the universe. By a long shot, actually, I think. We've got 2 to 200 atoms in the universe, if I remember. So it's completely infeasible to try to find two messages with the same digest after you run it through the hash function. And in Bitcoin type applications, and this is terminology you may not have heard much elsewhere, but it's what's beginning to get used, is we call this a commitment. So the idea is I have something on this side, that O, X, A, B, C, D, et cetera, that big long digest. But if I give you this, I have committed myself, because I'm saying, this digest corresponds to this other piece of data. And it's impossible for me now to go change what the data is. So when we look at, say, Bitcoin mining, well, your block, there you go. Your block header, well, one of the most important things in it is hash, and then so that's some of the most important things in your block header. Well, what's the prep hash? Well, it's just the previous block header. What's a Merkle root? Well, it's a famous, tree of transactions and so on. And because these are digests, our header commits to that data. Whatever number is in here, there's no way for me to go give you that number and then try to go give you a different previous block. Because I can't come up with two messages that correspond to the same digest. Or similarly with the Merkle root, well, I can't come up with two different sets of transactions that correspond to the same digest. And we call, again, we call that commitment. This data structure commits to that data structure and so on. And for those with more traditional comp sci background, you've probably heard of pointers. It's kind of similar in a sense. This is kind of the cryptographic equivalent to a pointer. We have something where making it possible to go and find something else. But there is a key difference, which is unless you have this data, you're never going to be able to start from here and figure out what that data is. Whereas a pointer, it's in memory. All right, go over there. So that's your first kind of thing. I think everyone kind of got that. Any questions? You think you could go program Bitcoin now? Well, so an interesting question. So if you just had hash functions, why couldn't you go program Bitcoin? What's the missing part?
Signatures, no?
All right, and why is that important?
Otherwise, anyone can spend anything, pretty much. Or,
Well, maybe here's a question with a hash function. Can I go and use a hash function to go and identify myself in a way where, I could decide what I want to spend later? Like, what if my PGP key was just a hash function? Would that be useful?
Only once?
Yeah. That's a bit of a trick question because you actually can't do signatures with hash functions. But no, I think you're basically right. And that because you committed in advance, you've already set history. So if my PGP key was a hash function, it'd be like I could only send one message, and I'd have to decide what the message was in advance. It's not terribly useful.
Is that why the Bitcoin address is a hash of a public key?
Yes, that's why we need the public key. So maybe I'll explain that now. And then, so what's our signature then? Well, usually we cryptographers like to talk about Alice and Bob. The more clever ones, they talk about Alice from Wonderland and Bob Marley. But let's see if I can draw this. Here, I'll try to draw Alice's square skirt. And I'm not going to draw Bob's unique identifier. But if Alice and Bob are communicating directly, well, sending a message is pretty easy, right? I mean, if I'm talking to you and you know who I am, when I go tell you something, you're going to know it came from me. Assuming you know what my voice sounds like and you know what it looks like and so on. The problem is when we're trying to go through a third party. And electronic devices are inherently third parties. I mean, that laptop is probably owned by the NSA 3 ways next to Sunday, and probably the KGB as well. So anything going through electronics, you can't really trust by default, and you can't trust as go over the internet and so on. So what we need is some way for Alice to convince Bob that the message is the same one she saw before, or he saw before. And well, if that's your message, let's meet at noon. She's implying we're going to meet at the Parliament building, blow it up. Well, how can she go convince Bob that these bytes are from her? And what a signature algorithm does is it lets her have this very confusingly named key, little thing move there. And if that's secret, well, through the magic of crypto, she can go and take this message and turn it into a signature. I've never been very good at drawing this, but essentially you can think of it's kind of like it's enclosing the signature, or the closing message, in that if any of this changes, well, this signature is now invalid. So if everything checks out, looks good. If I try to go and change this, let's meet at the moon instead, then this will show up as invalid. And that's really your basis of signature algorithms. You know, you have a message, you know that wherever the message came from on that signature, it came from something that had access to that secret. And as long as you go keep the secret, everything checks out. Now, of course, that key is me just a number. You know, I'm trying to figure out who it actually maps to. If it's the same Alice you thought it was, you run into tons of problems, but we can go over that later. But in the context of Bitcoin, it makes it very easy because I think, as most people know, Bitcoin addresses are ultimately just public keys. And that public key, well, the definition of who's allowed to send the money, you know, spend the money, is a person with a corresponding private key. Now, question here though is that sufficient to go and implement Bitcoin? You know, I have money, I can validly make a message that gives me, you know, shows my authorization to go and spend the money. I mean, what's wrong with that? Can't we build a system where, I don't know, maybe keep the messages around or something? Like, why is a signature insufficient for Bitcoin?
Because you can send the same message with the same signature to multiple people.
Same signature?
If it's the same message, it should be the same signature.
Well, if it's the same message, doesn't it do the same thing? I mean, it's just data. Why can't I go and
Yeah, but
send that message to tons of people?
you could send that message if you want multiple people. You could send that message, and
Okay.
they would all meet you at.
So let's say we have Bob, and let's say we have Charlie. Here, we'll make Bob smiley, make Charlie very unhappy. So, if you're Alice and you own Bitcoin, what's the thing that you're going to do to make Bob happy but make Charlie very unhappy in the future with just signatures?
Don't spend their money.
Okay, so how does that work? What's actually going on there?
You can create. Oh, sorry.
No, go ahead.
So we'll say, there. Let's get the coin. There's our very valuable Bitcoin. And in the context of the system we're imagining, if Alice makes a signature over this, that signature can then say, all right, say that Bitcoin, and who does it go to? And we put this whole message, signature, right? So we've identified what Bitcoin, we say where we want it to go, and we have a signature. Right? So, I mean, that looks valid. I mean, if the Bitcoin system can check that out, can verify, you know, that Bitcoin came from Alice, well, it's authorized to go to Bob. When Bob looks at that, Bob can say, yeah, signature checks out. Good to go. So what specifically is happening then in the double spend?
You can have another transaction to Charlie.
Sorry, what?
You can create another transaction to Charlie and then sign it as well.
Okay. So you're saying I could make exactly this, but Charlie, right? Well, so let's get more specific. So Alice gives Bob that message. Bob's convinced the message for Bob's real. Alice then gives a corresponding message to Charlie. Charlie's convinced the message is real. Right? We can imagine this like, you know, selling a house and I give you the title documents. Well, the interesting thing with this is the question really boils down to how does Charlie know that this is the only valid message out there? And equally, how does Bob know it's the only valid message out there? Because when you look at the messages, they're valid, everything checks out. But What Alice has done that's actually illegitimate is now there exists two messages. Call it the signature. And essentially, in our imagined system, well, everything's okay if there exists one message, but the moment there exists two, someone's defrauded someone. Problem facing designers of these systems is, well, how the heck do you know that there isn't another message out there? You know, I mean, how do you know that I haven't said something to someone?
Use a central ledger.
There you go. So we can, I mean, and this actually comes up in mortgages and house title, where there's two main competing kind of systems out there, the Torrens title system and it's called the common law title system, or deed title system, where in the deed system, I mean, in theory, the law is that any valid deed establishes chain of ownership, and if you create two deeds for the same property, well, then the law holders get paid a lot of money. And in the Torrens title system, well, we go say, well, we'll just have central register. My mom used to go work at a land titles office, so she was one of the people maintaining that central register. And with central register, the government keeps track of it. And if the government screws up, there's supposed to be some way to sue them and get compensated. But what's in that central register is the truth. You know, unless your title goes back to that central register, it's invalid, and that's that, and you can be defrauded. And the deed system, what actually happens is a bit screwy, because of course deeds can be counterfeited in the sense that, you know, I could go sell my house twice. So then you get title insurance companies, and title insurance companies, all they actually do is maintain a giant database of who owns what. And the more complete their database is, the higher the chance is that your house is real. So they're both systems end up being the same thing. Same problem in Bitcoin, but we have one small problem. Anyone who tried to operate that central registry would get in jail, like happens with the eGold people. So now our next step is figuring out, well, how do we go from this to actual Bitcoin? And it's kind of curious how the first thing that hashes actually leads to the second. And I'm sure most of you guys have probably heard something about mining. But I'll see if I can explain that a little better. There. So we had our hash function, right, where we mapped things. And what's neat about that is, well, if you think in terms of bits, right? So if I have, say, my message is up top, and I have there's here. Let's draw this better. So say these are the bits of the output of my hash function. I've drawn, what's that, 8 or something? The real ones are 256. And essentially every single bit is random, right? It can be a 1 or a 0. And so on and so forth. Well, this means if I want to go find a message that corresponds to digest, and suppose rather than accepting 1 or 0, I say it's B0. Maybe we'll say that has B0. Maybe that one has B0, and so on. Well, what's the chance of me finding a message that starts with 3 zeros?
Wants to power 8.
Yeah. So 1/8.
Yeah, one,
Right.
Yeah. It's power 3.
Every additional 0 I say decreases that chance. And if my message starts with, we call these nonces, and then like make that the rest of the message. Well, if I can pick that number, that nonce, arbitrarily, well, I can just keep trying new nonces until I hit a lucky number that has the right number of leading zeros. Well, it turns out this is very hard. I can burn a lot of energy. And now I've made finding that message arbitrarily expensive. Now, in reality, Bitcoin uses something a little different, which is rather says, here. Digest. Bitcoin doesn't actually use leading zeros, rather it uses a comparison. So we treat the digest as just a number and we see if it's less than the target. Well, as the target gets smaller, there's less possibilities for the digest to go satisfy that equation. An interesting fact is in really early Bitcoin, we actually have a copy of some pre-release code that Satoshi distributed some reviewers prior to the version 1 release. This was actually how it works. It was a leading number of bits. But its leading number of bits, well, your only adjustments are between, say, one more bit or one less, which is a jump of 2, and how hard it is. Well, in Bitcoin, these days, that target adjusts automatically based on number of blocks created in the past 10 minutes over a time period of 2 weeks. So this provides a lot of granularity. Right, as amount of hashing power goes up a little, we can adjust the target a little bit and keep things very precise. Old version of Bitcoin would be a jump of like 2, so you might go from a 5-minute block control to a 20-minute block control. I don't think anyone really likes that, so that's a better way, but conceptually this is pretty accurate. And getting back to, well, what's the purpose of this? Well, if this block header commits to transactions, previous block. Well, if we committed to other data in this, like we've said that the previous block is something, and we've said that the transactions at this state are something else, we can make it arbitrarily expensive to create a data structure. Because trying to go find that right nonce, well, we know it burns X amount of energy. And now if you want to change that data structure, as in I have one piece of data that sold my house to you, and I'd like to go convince him that he's also buying a valid house. Since we can make it arbitrarily expensive to change the data structure, we can make it expensive for me to lie. Because there's one version of history which consumed a ton of energy to create, and now if I want to change that history, I've got to destroy a ton of energy to create that alternate history. And that's really why double spending is hard in Bitcoin. The tricky bit's trying to figure out, why on earth would you go destroy all that energy? If I'm trying to go and give you a pizza, if it was just me destroying energy, well, what do I get out of stealing pizza from you? I mean, I steal maybe €5. That's good. How on earth are we going to make a system where I don't have an incentive to just go out and do that? Well, if we go take the entire world and combine their efforts into one proof of work. And what's nice about that is, well, people who want to do the valid thing, right, and want to not lie, well, you can think of all those honest people are one big group. And they can all work together. Because the honest thing to do is sign messages once. The dishonest thing is sign messages twice. But the majority of people are honest. They're signing one message, and they can take all their messages and put them together in one place. Then they can all pool their efforts, do a pile of work, destroy a ton of energy, and make it really hard for anyone in that group to then go on and lie and create a competing version of history where a message has been signed again. Well, fortunately, the way society seems to work is honest people can work together and dishonest people, it's a lot harder for them to coordinate because they're being dishonest and they're trying to get away with it. So hopefully that theory means that the proof of work works, and the individual user of a proof of work system pays a lot less than their security need. You know, because if I'm sending that pizza and it costs me, say, 1 cent to do my share of that proof of work, because say there's 500 other people working towards that same system, well, now it's actually feasible for me to send €5 when everyone else works together, you know, creates €5 worth of security for that one transaction. And that's pretty much your basis of Bitcoin there, but you know, I don't know where we want to go next. Do we want to talk about smart contracts? Do we want to?
Yeah, maybe.
Let's
I mean,
get some questions.
are your questions answered? Are there any questions?
Yeah, I have. Is this target used as a means to fit the commitment of one block in 10 minutes?
Yeah, yeah. So basically, for other reasons, we want the rate of blocks to be steady. I can explain that in a second, but since we want this rate to be steady, well, we make that target essentially be equal to the number such that for a given amount of hashing power, you would find one of these solutions every 10 minutes. And as for why you want this to be steady, well, what's interesting about this is this all about data propagation, right? Because if finding the block gives you an advantage, and it doesn't Bitcoin, you get a reward, well then presumably we want the system to be reasonably fair, in the sense that everyone who has some computing power, you know, uses it for the good of the network, they should all have an equal opportunity of turning the computing power into revenue in terms of blocks. Well, what would be an equal opportunity? I mean, let's suppose we didn't set 10 minutes. You know, you could go and find, like, say, 10 blocks a second, right? Well, if I'm not on a fast internet connection, I mean, how am I going to get the information I need to then add a new block to that chain? If I can't get that information because it's happening too quickly, then I can't participate. And now this mining process is unfair, and chances are I'm going to go take my computing power and just shut it off and leave.
So by getting the information, you refer to the transactions, or
Yes.
So you're collecting all the transactions over time.
Yeah, like essentially everything committed to under this field, you know, and all that data in the Bitcoin system. Everyone who wants to go mine has to have a copy of that data. And if we don't give people enough time to get that data, then the system's unfair because, well, you know, I may have hashing power, I don't actually have the data I need. Like, you know, concrete examples, if you find a block, right, and it takes 10 seconds for that data to get to me, I'm essentially wasting my efforts for 10 seconds, right? Because I don't know what I need to know to build on top of it. You know, when I go create that block, I'll be a block behind.
What I find very hard to imagine is when do you start and when do you right, start is easy because the first transaction is the actual reward of the miner for validating the previous block. But where do you stop collecting transactions, finding this magic number?
Yeah, well, what actually happens is miners, because blocks are limited in size, you know, every time they get a new transaction, they really have a decision. I mean, what would make me the most money? And if your block is already filled with transactions that pay a higher fee per byte of data than the one I just got in, I'm not even going to add it to my block, right? Because I can't improve my revenue by putting that transaction in. So it's not like there is a stopping point, it's just a continuous process.
Right. So you can decide, well, the miner decides with his own protocols whether
Yeah.
he collects
Yeah.
more transactions to find it.
Yeah, it's all just based on what you know at any moment. You know, and the actual hardware itself, like, you know, this thing's like a Bitcoin miner, or I really should say Bitcoin hasher. You know, I might have my computer and there's a certain amount of latency to go to it saying, all right, you start working on something new. Because this piece of hardware, the ASIC, doesn't actually know anything but the block, but it does still have to know, what are these numbers? And it takes some amount of time to go transmit new numbers to it until it starts working on new work, as it's called. But that's just kind of a continuous process, other than those latencies. Essentially, every time I get a new transaction, I'll make the decision, do I add it to my block? If I do, I'll update that work, and things just go from there. And if I get lucky, which is a Poisson process, it's just random chance that on average is every 10 minutes, and I get that result back, I know what knots I need, I know what other numbers I need, and I quickly propagate to the network, telling everyone as fast as possible, hey, I found a block, you should go and work on top of it.
So the only reason why you would collect more transactions in the ongoing block is the fact that you get a better reward for it afterwards.
Yeah, they all pay money basically.
Sorry?
They all pay money basically,
Yeah.
right? Because you've got that fee attached. Now, an interesting subtle thing about this as well, this gets into block size debate stuff. If there wasn't a limit, right, and I'm the guy with a fair bit of hashing power and a fast internet connection to everyone, and you're not, what's in my incentive to do to make the most money in the long run? Should I add more transactions to my blocks or less? Why?
Because you're gonna screw the competition, because they cannot receive your blocks fast enough to blow them up with you.
Yeah. This is what makes my job hard. Like we could imagine, but draw this. There. So if we imagine USA being, as usual, very patriotic, and China, well, between the two, you've got the Great Firewall of China, and data passing from one side to another passes quite slowly. Well, if we're at this point, right, where we have a bunch of blocks, and this would extend back to the Genesis block. Well, depending on who finds what block, you can imagine, let's just say this is B4. All right, if we find a block here, well, let's look at what we're seeing here. So these arrows mean commitment, right? So there's a digest number in here that committed to this result, commits to that, and commits to that. So this block, nothing can be changed. Remember, this is just data. So when someone finds this data that's a valid block, it's going to take time for that data to get to the US. And maybe like 5 seconds later, right, now people in the US have the data. Remember, this is data, so this and this, they're equivalent, right? Same bits, they mean the same thing, but they're in different places. Everything over here, everyone has a copy. But in here, it took time for that data to get to there. I cannot draw dashes there. Slowly propagating over. Well, who has how much hashing power? I mean, right now, China has like, on the order of, I think, 60%. US exactly probably has like 10%, and Europe has another percentage, and so on and so forth. Well, what's the most likely thing to happen? Rather than the US finding that next block, China will probably find another block, B6. And if this happens, say, 10 seconds after, there's a certain chance that someone in the US Might find another competing block. We'll call it B6B, B6A. And if the Chinese guys find yet another block, by the time this data gets anywhere else, right, the rest of the world is going to ignore it because it's not the chain with most work. And when this data finally gets over here, well, it gets canceled. Now we have B6A, B7, and whoever found that, they've now wasted their effort and lost out on however many bitcoins that block represented. Yeah, so that really gets down to like why this fairness matters, because the faster that interval between blocks, the less time it's you have available for other people to get the data. And as an example, we've seen altcoins, try to push that number down really low, like to a couple seconds. And usually what happens is the network doesn't really stay in consensus, and you end up with a lot of hashing power in a small number of places because it's just not profitable to be the guy elsewhere. So that should answer your question for where that number comes from. Obviously, there's a fair bit of controversy around what those numbers should be, but these aren't technical questions, they're political questions. It's a question of fairness, not a question of what the tech really does.
Is that principle specific for Bitcoin, or is it for blockchain? Is it for other currencies also?
It's specific to proof of work systems. Probably also proof of stake systems. Like anything where there's people who potentially have an advantage in getting data sooner or later. And this wouldn't at all be true in, for instance, one of these so-called bank chains, right, where you have one entity or a small number of entities aren't really competing with each other. They're supposed to all have all the same data. And I could probably explain what would that look like. These so-called bank chain systems, you might, for instance, just have there.
Yeah, you were talking about the private blockchains.
Yeah.
Okay.
My bank is very modern. It has a nice flat roof, a little front door, and there you go. And if these guys have a chain, it doesn't matter when the data gets to them. They're the bank. They don't care. They don't have competition. Now, if there's two of them, I'll give an ultra-modern bank with many, many floors and a big antenna at the top. If there's two of them, depending on their business relationship, chances are the way it works is just they both sign off. You go say, well, if that's your blockchain, so on. For each of these, you've essentially got two check marks, right? Kind of saying there's two signatures. And both parties in the arrangement have to sign off. But again, a system like this, what does it matter if one bank gets the data a little before the other? The system just isn't valid until they both check off. So there's no issues there. There's no incentive to do anything essentially, but just uphold your business agreements. So maybe an interesting question I could then give here is, if we want to talk a bit about how these systems work, is you might ask, well, why would you even have a chain at all? If we can put transactions in here, we can go through all the motions, but
In just a kind of side question, does Ethereum actually have a blockchain like Bitcoin has?
it does. Yeah.
Okay.
But what's in it is interesting, because on Ethereum, you've got code, right? Well, the sort of the marketing idea of what Ethereum is, right? Is this computer. And you've got Turing complete computer. It runs code. It runs contracts, and then presumably the contracts have memory. Because if they didn't, it wouldn't be much of a computer. And
You have storage.
Yeah, you have storage. And
Yeah, you mean that every contract that has ever been run somehow has to end up on some blockchain?
yeah,
Or is that the big question?
well, because your blocks in the Ethereum world, they're committing to states of execution. So it's kind of like you have a computer, and every few minutes you checkpoint it, and you say, all right, we will find the entire state of everything that's running, all the memory and all the values and so on. We'll hash it all up, and now we have one value that commits to that state of computation. And that's a little strange because, first of all, you might want to ask, what's the actual purpose of that? Why I can run computations on my own computer? Why do I need Ethereum to do this? Wouldn't it be faster and cheaper to just run things at, 3 gigahertz rather than one block every 20 seconds? Which I think Ethereum's every 15 seconds, if I remember. 14, yeah. So it's not, that part isn't totally clear. But, this is marketing literature. It's not what's really going on. What's really going on is all about storage and the state. Because the big thing that Ethereum blocks commit to is the state of the storage for the contracts at every block. So if I write a contract that, say, processes mortgage applications or something, when someone adds a message to the Ethereum state representing, the part where I'm applying for a mortgage, well, it could checkpoint that into the state. And then when the contract executes and approves my application, we'll go and checkpoint that state and so on. And I can write my code around that. And once I'm applied for a mortgage, in the case of the mortgage, it's probably fairly important that I can only apply once. So once it's applied, it's irrevocable. And I think it's fair to say the point of Ethereum is really about making those state transitions irrevocable. I have a lot of disagreements with Ethereum. I think there's much better ways to go do this than imagining some crazy computer. But you got to admit, just like cloud computing, the model for a programmer, I write a program, and it's simple, imperative program. It does this, it does this, it does this, and it executes one line after another, and state gets updated. That's a really simple model to work with. It's why the Ethereum equivalent of Hello World is, let's go make distributed DNS, and they do it in 5 lines of code and they put it on a t-shirt. It's very seductive, looks very nice, but
with comparative programming, you mean a serial
yes,
top-down code?
Exactly.
Okay.
Yeah.
Does that have anything to do with the von Neumann model?
Von Neumann model?
Yeah, sorry.
Yes, it is.
Okay.
That's exactly what it is. I'll give you an example. So Ethereum, let's see, how can I write this? Ethereum DNS could be something as simple as, all right, we'll say function, loop, all right, and it takes in a new message. And if message equals new name, then, snap. So you can imagine Ethereum contract being got this loop, and every block that executes takes in messages. Well, if the message is the new name command, then we just register that name and we update this map. What could be simpler? It's very easy programming model. You just do things and it does stuff, and that's that. Not a big deal. I'd love to have stuff with who's allowed to create new names and so on, but figuring out how to do that stuff is fairly easy compared to, I think, a much bigger problem, which is how the heck do we make this like scalable? You know, if we have a million of these new names at once, does that mean like every node in the Ethereum network needs to process a million new name operations? You know, for every block? I mean, what if I want to do something else as well? And trying to figure out like how do you make this scale? How do you split that data across multiple systems?
Yeah, you mean that's what they are now doing is they are actually building the traditional computer in a distributed sense, but the computer itself logically is traditional. But once you have a cloud computer, there are a lot of new interesting things you really would like to do with it, but it's not they don't have a solution for that at this moment at least.
Yeah. And you know, I think cloud computing is a good analogy there, where when you've looked at what's happening in cloud computing, I mean, prior to that, you know, well, how am I going to make a database that like does 1 million transactions per second? I'm probably going to call Oracle and I'm going to pay them a boatload of money. They're going to ship me some magical piece of silicon that does great things. But in cloud computing, like there's no nice piece of silicon. They're all like crappy computers, no more powerful than your cell phone. But there's a whole lot of them, and that's where all the magic is. Figuring out, well, how do you go take that task and spread it across many different systems? In Ethereum, because the model is this, my argument with Ethereum is it's going to be very, very difficult for them to figure out how do you map this ease of use, this ease of programming model to something where it's actually spread across multiple systems. You know, like as an example, you can imagine in a more traditional database making the system scale by saying, well, rather than putting all the names in one mapping, right, we might just split them up. We might say everything starting with A and B and C and D and so on. Right, we'll split them up into shards. And rather than having saying that's loop, we will say loop A for all the names starting with A. You know, and so on and so forth. But like just the fact that I tried to go split it up and make things scale better, I mean, I'm doing a heck of a lot more work. You know, now I've got 26 different loops. Well, I hate to say this, but my suspicion is what we're going to see is programmers write Ethereum contracts that seem really easy. They don't scale, and they'll just spend a huge amount of effort trying to then improve the scalability and then make them run faster. And even that's kind of ignoring things because it's still got a question: how does the Ethereum network deal with this? Like we have 26 different functions, different tasks for my, DNS service. It's not really clear how does that get mapped to different parts of the Ethereum consensus. I mean, do we split up the consensus? I think they've got a lot of research questions over it.
Because at the moment, all the miners need to run all the contracts basically to see if it stays the same as someone else.
That's exactly it. Yeah.
I listen a lot to Bitcoin Censored, and they are all the time talking about this. And I was also very skeptical, but in my search for some Japanese guy some weeks ago, I stumbled upon an article by Ian Grigg, and it was interesting. He wrote about verifiable computing.
Yeah.
You read it?
I used to work with him at R3.
Yeah. And it was interesting because it made me look at it another way. Just to say that this, I heard about this year end of 2013, and there was a lot of buzz, but it took me 2 years to understand what it actually was because of all the buzz and what I actually heard about it, what it actually was, didn't match the buzz. So I was, what is it exactly? And now I realize that it is just, let's say, Bitcoin, but a lot worse in the sense that where Bitcoin is distributing the...
Where Bitcoin already sucks a bit.
Yeah, yeah.
Makes the problem.
Where Bitcoin sucks is the ledger on every machine, which was exactly what I didn't believe would work with Bitcoin in the beginning, because I thought this is totally, it's totally undoable. So when I realized how Ethereum worked, it was really, it was, it was kind of a disappointment. But what I found interesting about Ian Grigg's story about verifiable computing was that he was talking about that, or exactly what you also said, that you can't trust computers, but you can make it more difficult to let computers make errors if 50 computers at the same time do it.
Yeah.
So like with the spaceship program, every spaceship system has 5 computers, each two doing the same tasks, and then they are voting.
Yeah.
So let's say they have a small blockchain of 5 computers, and they vote between each other. If 4 computers say A is the answer instead of B, then A is the answer.
Yeah.
But if 3 computers say A is the answer, 2 say B, then still A is the answer. But you get the idea. But what I found interesting about it is that, when you would have said 20 years ago that little JavaScript applet would turn out into a complete operating system in the browser, also nobody would have believed it. And that's how I look now at. I understand the skepticism against the Ethereum model, to say like that.
Yeah.
And I'm not sure. I don't know about Turing complete. I'm not an expert on that. But I was thinking. What if you could provide a trustless cloud?
Yeah.
Because cloud is by definition at this moment trusted, but what if you could provide a trustless cloud? The idea, at least, would be very interesting.
It's very seductive kind of idea.
Mm-hmm. Yeah.
Well, I think your real problem is, and you see this with like voting schemes in high reliability computing. At what point does your overhead become bigger than just running it locally?
Mm-hmm.
Like with the NASA example, the space shuttle computing system is a little crazy because you mentioned like at 5. Well, what that 5 is, I believe it was 3 of them are a 2 out of 3 voting scheme, all running the same software, and then they have another 2 computers, or it might just be 1 computer, I forget which, that runs completely different software, written from scratch to do the same thing by a different team.
And there is another computing checking the system all the time.
There isn't actually.
Oh. Okay.
So the really interesting thing with the NASA scheme is, well, how does the voting actually work? Well, you've got wings, you've got flaps on the wings,
Mm-hmm.
and the output of the votes, is ultimately, hydraulic actuators act on the lifting surfaces. And they simply make the actuators powerful enough that if 2 out of 3 computers vote the same way, it goes this way. Because the computers that disagreed are physically overpowered by the computers that all agreed in unison.
But do you also mean that if they vote unisono, that there is more power than if they vote 2 out of 3?
The thing is, the actual actuators, they all know what, like the sensors that determine what aim the actual physical lifting surface moved, and that's a closed loop, right? So it doesn't matter like how many hydraulic pistons try to move something, it'll always end up in the same place. But what's important is that if the hydraulic pistons disagree, the ones that are in the minority get physically overpowered by the ones that are in the majority. And then the 3 and then the 2 of 2 system, that's, if I remember correctly, literally a switch that you flip that can disable the hydraulic actuators for the 3 out of 3 if the software was wrong. So hopefully the pilot's in a position where they'll recognize, all right, maybe the primary software is wrong, let's switch to backup software and hopefully that'll continue working.
But those computers, are they analog or digital?
I believe in the beginning, and I may be misremembering this, one set was digital, one set was analog. Like it used to be quite common for flight computers to have a digital primary and then analog backup. Although by the time the shuttle retired, they may have switched to digital on both sides, or maybe digital on both sides to begin with. I'd have to check the history again, but it is very common, or at least used to be, for there to be a digital primary and analog backup. Like I'm 90% sure the Concorde did this, where the digital computers at the time they weren't sure if they were reliable, so they had the analog backup. But it's interesting. I find it most interesting the solution for voting, where in a lot of these systems, the voting circuits are the things that fail because they're a single point of failure. Well, how do you make them not a single point of failure? You don't have one.
Mm-hmm.
The reliability of like mechanical hydraulic controls overpowering each other is very high in a way that electronic circuit isn't. So they just stuck with one system overpowering the other. And then the concepts like blockchain tech, I mean, I don't think anyone really has an application where you need that many computations. Maybe we should do actually.
But I mean, it could end up like Bitcoin in the sense that, I mean, I'm not running a full node on my mobile, not yet, certainly yet. But and I also don't think that in the end, I mean, it would be bullshit for the whole world to record a free coffee transaction. So I think that in the end there will be kind of like an economic balancing. And I could imagine that with the Ethereum world computer that you also need something like, I don't know how. Oh, I remember you on Twitter asking about it for an SPV kind of client or something.
Yeah.
For the DAO or the Ethereum.
Yeah, well, this is actually Andrew Miller. He was asking about that.
But I think one of the ideas with sharding is that you can even completely ignore some shards.
Yes.
Yeah, so you can make, because you can make an unlimited number of shards. You could even make shard for a certain application, and the rest of the world doesn't even have to look at it. Yeah, it's just, you create sort of an automatic sidechain.
Of course.
Because it's just all in the same space, but you don't look at it because you don't care what's happening in that shard.
Of course,
because it's for an application that you don't care about.
But there's a balance to those ideas. Like at some point, what exactly is your security model? I mean, if nobody else looks at it, does that mean I can get away with fraud?
Yeah, you mean the sharding goes against the idea?
Yeah.
So sharding is kind of like the SPV translation of Ethereum.
Well, as an example, I mean, if you assume that some percentage of miners are honest, a lot of these problems become really, really simple.
Mm-hmm.
Right? Because, I mean, if in this room, if I make the assumption that 10% of people, what do we got here, 12 people or something?
Mm-hmm.
If I make the assumption that, say, 1/3 of people are honest, I can go write a protocol which says, well, I will go poll, and if I can construct it so that if the honest people could tell me something, like, was this thing double spent? Often, I can construct protocols where a very small honest minority will still make the protocol work. Right? In the case of the double spend, I mean, the existence of a double spend is proof of fraud. So if I'm receiving a house, all I need is one person to go tell me, oh, by the way, it was already sold, and I'm okay. And if like 1 out of 100 miners are honest, well, I will just go sample sufficiently enough to get 99% reliability, even if I have to do like 1,000 samples to find that 1% who are honest.
Yeah, you mean the fact that that already 80 people have said that there was no double spend. That's not interesting. It's interesting that there is someone mentioning there is a double spend.
Yeah, I only need that one person to go tell me.
Yeah.
And the protocol still works.
But then you have kind of like the problem of nu je dat als iemand iets wil laten vastlopen, hoe zeg je dat?
Adversaries.
But I can design a protocol in many cases where I will know for sure that I've sampled it out of the full set. I mean, 1 out of 10 is an easier example where, every time I sample, right, my protocol can essentially say there's two things that happened. One is I got a return, and the other one is I got DOS attacked, right? And I didn't get a reply. And the didn't get a reply thing, it's just proof that maybe someone's defrauding me and I just stop. If I get a return back, if I make the assumption, say 1 out of 10 are honest, well, I just keep doing this over and over again until the probability of not hitting an honest person is sufficiently low that I'm okay to take the risk. You know, and 1 out of...
You also need to know how many persons are participating.
Yeah, well, that's a tricky one. Like, if I make some assumption that seems low enough, I guess my point is that maybe that's the way, but if I can make that assumption, right, the protocol becomes simple. If I can't make that assumption, the protocol becomes way harder because I got to set up economic incentives and all this magic. And that's really the problem Bitcoin has. I mean, well, you could ask, like, why do we need all this blockchain stuff? Why can't we just assume that some computer is going to tell me about the dollar spend? Well, in the Bitcoin model, we assume that everyone we're talking to could be lying to us. You know, every single computer that our node is talking to could be lying. And the proof of work makes that lie computationally expensive. Not just like difficult, but like actual provably computationally expensive. So even if everyone around you is lying, it's still difficult for them to spend. Whereas if we didn't do that, if we had that, you know, all right, I can go and sample 100 computers on the internet, at least one of them is going to tell me the truth, we wouldn't need proof of work. The problem would become actually a lot easier. So it's kind of interesting that, you know, and I think, you know, going back to like the sharding stuff, a lot of these sort of sharding ideas, again, become very easy if you can assume that fraud will get propagated. You know, if I go split up this DNS system into like A, B, C, and D, well, if I'm mining the A chain, so to speak, and the A chain depends on these other chains being valid, if I assume that if someone detects fraud, they'll propagate it around the network, right, and I have a certain percentage chance of seeing that fraud, this becomes quite easy, right, because I can run the numbers to figure out, well, what's the reliability and so on. But in a security system, I mean, maybe A, B, C, and D are all colluding against you, and they're trying to defraud you.
I'm actually wondering if you don't do you. I have the feeling that Bitcoin has way too much security at the moment, and I mean it has to do also with the the internalization externalization discussion of the mining power, and the question whether a transaction really. I mean I know there are stories of people saying that an actual Bitcoin transaction should actually be $20 or something, which I think is
$3 right now. It's like 3 or 5.
Yeah. It's 35.
Like $3 to $5.
And that's the result of the Chinese miners who are actually kind of subsidizing it.
Well, it's not the subsidizing, it's the result of inflation rate. Right? Because Bitcoin's still inflating the currency supply by like 8% a year or 10% a year right now.
But isn't it the case that I would say if I would be a miner and I would believe in Bitcoin, this is the moment to make the big.
But remember, it's not a subsidy. Mm-hmm. Or I should say, the miners aren't the one doing the subsidizing it. They're not losing money on this. So, I mean, to a great extent, I mean, maybe a little bit. The subsidy is coming from the inflation rate.
Okay.
Right. That's where the money's coming from. Every single Bitcoin owner, a chunk of their money per year is going to miners, regardless of how many transactions they do. So if you have 100 Bitcoins, well, in 1 year at the current inflation rate, which will drop in half, of course, fairly soon, but that would be like 8 Bitcoins just going to pay for security. You can do a lot of transactions for 8 Bitcoins worth of value. Get at the current like 5 cents per transaction fee. And that's where that security is coming from. Now, if we change the inflation rate, that'd be a different question. And maybe per transaction it would cost less. Like the moment the halving happens, well, our per transaction security cost is going to immediately go down by about half. If a transaction on average takes like 5 cents worth of fees to accomplish, And then the inflation subsidy corresponds to another, say, $5 worth of expense. Well, now we have a transaction cost, $2.50. So, but I mean, the problem is, like, it's, how do you go pick how much security you need? You don't know until it's too late. It's like trying to go decide, like, how good of bars should you go put on your window? Well, if everyone lives in the same house, and all their stuff's gonna get stolen when the window gets broken into, I mean, you're just not gonna know. And we don't have, like, stats for, say, 51% tax. It's not like a normal case where we say, well, yeah, 10 houses per year in this region got broken into. I mean, we just don't know. Bitcoin, when it gets attacked, will be the first thing ever attacked on that kind of scale. And we don't know how big our attackers are, so I don't really have a good answer to that. My guess is you could probably say something like, if Bitcoin can't afford to pay, say 1% of the value of all Bitcoins per year for security, the whole system's probably infeasible. But I can't say that 1% is enough or too much or too little. I can just go pick a number out of thin air and hope. Why don't we take a break and maybe talk a bit about the smart contract stuff?